Hello, everybody. Welcome to the second part of section 6.2. Now we're talking about trigonometric substitution. Um, in some sense, one can say that the trigonometric integrals is exactly a preparation for this type of substitution. Because if you think about it, the trigonometric integrals, at least majority of it, doesn't even require Calc 2 material, right? Majority of it is just some trig identity, some U substitution, right? Calc 1 stuff at most, right? Other than the very last difficult case, of course, that uses the integration by parts. So in some sense, the 6.1, 6.2a part A is not really Calc 2 material, but it prepares you for this section, okay? This particular technique. Now where almost entirely new territory here. Trigonometric substitution is great in dealing with radicals, and radical functions shows up quite often in mathematics, so we would love to be able to deal with that in terms of integration. And the way we handle this is to actually rely on the identities, right? The trigonometric identity, in fact, specifically the Pythagorean identity. There's three versions of it, depends on which one we're looking at, right? We have it on the rightmost column of this chart here. We're gonna base off of these three reasoning, these three versions of the Pythagorean identity to come up with a substitution that allows us to handle radical functions. And the biggest way to distinguish these is to ask yourself, where is the function and where is the constant? So the first, a squared, a is the constant here, right? So constant minus function. So constant square minus function square. We use sine. The addition is easy because that's the only one. So function plus function square plus number square, or number square plus function square, they're all the same. We use tangent. Function square minus number square, which is the opposite, right? Which is the opposite in this one here, than the first one. That one requires secant. Okay, so again, number square minus function square, we use sine. Function square plus number square, we use tangent. Function square minus constant square, we use secant. The range of data here, this is just kind of good to know where the substitution come from. But these are literally uh, the um, the domain of the inverse trig functions. So that's where they're derived, and that's in some sense that's what they're used for. So you don't have to worry too much about these. We can majority of the time apply this technique without really focusing on it. There's only a couple of niche details that you may want to consider the range of data um, when you're doing this kind of substitution. But majority of the times it's just a kind of a good to know base. Anyway, so let's practice some of these. Okay, just like the uh, trigonometric integrals, the idea is to understand which case you're using, right? And then which kind of radical function that you see inside your integrand, and then you can apply the substitution correspondingly with your chart. So let's take a look at our first problem here. Um, oh, and of course, important, right? This is what I mentioned in the previous video. If you do not have a habit of writing down the dx or d whatever, you're definitely going to make mistakes here. I myself have suffered through that many times due to laziness, right? This is like a math people's worst nightmare, or worst enemy is essentially laziness and hand waviness a lot of times. So do be careful on that. So let's come back to this example here. Now, when you look inside that radical, you see x squared minus 25. So a function squared minus a number squared, right? Of course, the 25, maybe I'll write it here. 25 is 5 squared, so this is just x squared minus 5 squared. So function squared minus number squared, right? In this case, more specifically, that the number is also 8. sorry, the number is 5, right? A is equal to 5 here. Okay, so basically I know I'm using this case, which means I'm using the substitution x equals to a secant theta. So I'm using, that's all I need to identify which type of substitution I'm using. But let's take a look at how this substitution is going to play out. We're going to go ahead and say, we're going to let, say, x equals to 5 secant theta. That means dx equals to 5 secant theta tangent theta, right? Derivative of secant, d theta. Now, this is where writing the dx is so important, because that little dx all of a sudden have that much piece of information. So if you think this is just some some bit of stuff that as part of your notation that you don't need to write down, as long as you remember what variable you're working with, now is no longer the case. You're going to have a lot of information incorporated into that dx. So if you don't write it, you're definitely going to get this wrong. Anyways, going back to that substitution, apply my substitution here. This is going to give me the integral 1 over x to the 4th, but now x is 5 secant theta. So 5 secant theta to the 4th power. I have square root of 5 secant theta squared minus 25 dx. Oops, not dx. They almost made that same mistake that I was just talking about. That dx becomes 5 secant theta tangent theta d theta. Boy, this just turned into a big deal here. Okay, so after the substitution, this is what my integral looks like. So it actually looks more complicated, right? A lot more complicated. But lucky for you guys, you already know how trig functions work, right? It will get more complicated before the simplifications start to kick in, and then it's actually going to make your integral a lot more simpler as you progress to simplify your trig functions. We can leverage a couple of things here. For one, we can take a look at how many 5s we have out, right? I got 1 here on the top, on the numerator, but I got 5 on the bottom, but I have 4 of those. Okay, so collectively I have 1 on the top and 4 on the bottom, so I can simplify that into just simply 1 over 5 to the 3rd on the bottom. Take all of those out, I can actually cancel one more thing, right? I got a theta here, theta. I got secant of theta there, and I got 4 copies of secant theta there, so I can get rid of some as well. Okay, so for the next step, the numerator just becomes tangent theta, because the 5 is gone and the secant theta is gone. And then now on the bottom, I have secant cubed theta, right? Again, there was 4, and I cancel 1 from the top. Okay, so inside the radical, though, the square affects the 5 and the secant. So I got 25 secant squared theta minus 25 d theta. Okay, and what I can do there is I can go ahead and factor out a 25 from the bottom, right? Just kind of imagine from the bottom, factor out the 25, and then I can then take that 25 out of my radical and essentially get another 5 on the denominator. So I have, next line, 1 over 5 to the 4th power, because I have another factor of 5 from the denominator. But then the function becomes tangent theta over secant cubed theta square root of secant squared theta minus 1, right, after taking out the 25. But I'm kind of hoping you kind of see where I'm going with that, because because what we have now is the Pythagorean identity. And secant squared theta minus 1 is also known as tangent squared theta. Okay, this is exactly where the thing becomes really, really nice, right? And really the reason why we make these kind of substitutions is it allow us to get rid of that radical. Okay? It allow us to get rid of that radical. Square and the square root cancels out. In fact, in this particular case, when you take the square root, just highlight that real quick. When you take the square root of tangent, you just get tangent. So that's going to cancel out with this tangent on the top. So this whole integral actually just becomes 1 over 5 to the 4th integral of 1 over secant cubed x cubed theta d theta. Okay. And if you already watched the previous video, you know that secant cubed theta is very, very difficult. Does that mean 1 over secant cubed theta is also very difficult? It absolutely does not, because 1 over secant is also known as cosine. This is also kind of what I mentioned about last time. Once you have see a couple of basic interactions, every time you have negative exponents, right, you can just revert that to a different trig function to get rid of that negative exponent. So secant cubed on the bottom actually just becomes cosine cubed theta d theta. And this goes back into the case where cosine is odd, so we just take out a copy. So we write that as cosine squared theta, cosine theta d theta. Okay, and I'm hoping you kind of remember that we're supposed to use sine here. So I'm going to rewrite that cosine square as 1 minus sine squared theta, cosine theta d theta. Okay, at this point, our usual substitution, right, given to you in the previous video or notes, u equals to sine theta, so du equals to cosine theta d theta. So this whole integral, once again, transform into 1 over 5 to the 4th power integral 1 minus u squared du. And that is a easy integral, which is actually, 5 to the 4th power is 1 over 625. Let's leave it like that. But the integral becomes u minus u to the 3rd over 3. And I'll just write the plus c on the side here. We talked about that before. Okay, so that's at least how we do the integral. Now, the small issue here with this type of problem is you actually have to convert it back into the letter you started with, right? I did not start a problem with u. I did not even start a problem with theta. I have to convert this back into x. So that's the other challenge of this kind of problem. You got to remember to do that. Okay, so let me make this a little bit smaller here. Okay, uh, let's do some back substitute. So it's easy to take, take the answer back into theta. So I have 1 over, let's go ahead and distribute out the constant here. Nah, you know what, actually, just leave it. So 1 over 625. U just becomes sine, so sine theta minus sine cubed theta over 3 plus c. Okay, so now I need to get rid of the sine and, well, write it in term of in term of x. How do I do that though? Right, that is actually kind of challenging now because my substitution isn't as straightforward. My relationship between sine and theta is here. This is my substitution. So what do I have to do here? This is where your trigonometric technique kind of comes in. Uh, roughly around section, I believe 3.5, there was a topic about this. You can go back and review that a little bit too if you like. But the idea here is we're gonna leverage this. So maybe I'll draw this on the side here. So if x is equal to 5 secant theta, if I divide 5 on both sides, then x over 5 is equal to secant theta. From here, I can construct my right triangle. Label your theta. Secant is hypotenuse over adjacent. Maybe it's also a good idea to go back and review a couple of these definitions. Secant is hypotenuse over adjacent. So by Pythagorean theorem, I can then calculate the third side. I believe you all know what the Pythagorean theorem is. So this is just going to be x squared minus 5 squared, which is 25. And that's kind of maybe a quick check. If the radical doesn't show up in your original question, you see that x squared, square root of x squared minus 25. If that radical does not show up in your original question, maybe something has gone wrong. Yeah, that's a big that's the first I guess obvious indication that something has gone wrong. So you should definitely double check. But anyways, as soon as I construct this triangle, I can then relate theta, x, and sine more, together. So in this case, we got sine theta equals to opposite over hypotenuse. So I got square root of x squared minus 25 all over x. So that is what my sine function looks like. And now it's just gonna be a big old, big old solution written out very, very carefully. So the final answer for this problem is just going to be square root, is just equal to 1 over 625. You don't have to worry about distribution here if you don't really want to. Sine theta is this whole big old radical thing, so x squared minus 25 over x minus, I'll just put it as a 1/3 in the front, save me a little bit of spacing here, radical x squared minus 25 over x to the third power plus c. And that, ladies and gents, is the final answer for this problem. It's definitely a doozy, right? It's definitely a long problem here, and no surprisingly, because of the amount of steps that we have, really has a lot of room for error, right? But ultimately, this is the right method to do this kind of problem. At least it gave you a way to do a problem like these, which is definitely not accessible for you during your Calc 1 days. Okay, so this is the trig substitution that we're working with, and really, unfortunately, most of these kind of problems are gonna be similar in length. So, um, so yeah, just be aware that these kind of problems do tend to run pretty long. I kind of already said it at the beginning of the course. Sometimes these kind of problems are, easily uh, like 2 pages long, or at least a full page, right? Assuming you have everything spaced out carefully, um, you're definitely going to have a little bit of uh, a little bit of writing to do for this kind of questions. Okay.